Alright, so what we're going to do now is we're going to prove the binomial theorem. Alright, and we're going to do sort of the traditional one. Again, we'll do a different proof of this as well, but in this video we're going to prove it using induction. Binomial theorem is really an equation. If I had a lot of extra room, I'd write out some extra words here, but oops, try to keep things concise where I can keep them concise. So what it does is it claims what the expansion of 1 plus x to the n is. All right, and so it's a summation from k going from 0 to n of, these are x to the k powers, right? And so we said in a previous video that the n choose k's are the coefficients of x to the k and 1 plus x to the n, right? So this is saying it using sort of mathematical formulae, right? N choose k is the coefficient of x to the k in 1 plus x to the n, right? And so I think it's necessary, considering that you may not have a ton of experience with summations, to realize this is a shortcut to just writing n choose 0 x to the 0 plus n choose 1 x to the 1 plus dot dot dot. The last two terms would be n choose k minus 1 x to the k minus, sorry. I always do this, it's not k minus 1, it's n choose 1. I'll use enough eraser here to get this cleaned up. There we go, short. So n choose n minus 1, x to the n minus 1, and then the last term is n choose n, x to the n. Alright, you can see it uses a massive amount of space, but the book does sort of mix these up. It'll occasionally do this, or occasionally do the second one, and it kind of mixes them up. So keep in mind, you can kind of, or you really can do either. This is just as much more efficient with space. Okay, so just because I have this dead space here, I want to use it for something important. I want to help us remember from the sort of that previous theorem, the Pascal's triangle theorem, if you want to give it a name, that n choose k plus n choose k plus 1 equals n plus 1 choose k plus 1. Remember, so we proved this previously. Alright, so here's the binomial theorem, two versions. And this is a previous sort of theorem, or a little preposition or corollary, or whatever you want to label that. All right, so to prove this, we're going to use induction. And because there's so many variables here, it's kind of nice for the reader to know what are you using induction on. And then a lot you could, but we're going to use induction on n. Right, and what makes this, it may be one thing that adds difficulty that's really an artificial difficulty, but still difficult, is the fact that there are x's, n's, and k's, and summations, and there's just a lot of symbols going on. But keep in mind, we're really just doing a calculation where we're trying to crank the n from n to n plus 1. Okay, now for induction though, of course we need a base case. So let's use complete sentences here. So for our base case, okay, I usually ask the class which one they want to use, but n choose 0 is the one I'll choose. It's the sort of the most fundamental case. What we have to do is show that it's true. We actually have to do the calculation. We have to check that the left-hand side and the right-hand side are equal. So base case n equals 0. Let's go ahead and get the left-hand side done. 1 plus x to the 0 is equal to 1, right? Okay, so that's the left-hand side. For the right-hand side, you kind of have to start with words to get a sentence started. We have, it's a summation. It's a very short summation, k going from 0 to 0, which tells us there's only one term. N is 0, so it's 0 choose 0. Sorry, 0 choose k, excuse me. We'll be that in a second. X to the k. Okay, pause for a second, right? The k is always the index, that'll be there. at least in this summation here, and n is equal to 0. So in this case, this is a summation with one term. That single term is 0 to 0, x to the 0, which is 1. All right, let's make sure this settles in right. Our base case is quite simple. We use the exponents are lots of zeros, basically all that's present, and we have 1 equals 1 for that. Okay, so the magic of induction, not that it's magic, it's logic actually, is that we're going to assume it's true for the nth case and show that it implies the next one, right? And so this gives us a mechanism to move from 0 to 1, 1 to 2, 2 to 3, in fact to any case we were interested in. So we will assume the theorem is true for n and show it implies that it is true for n plus 1. All right, now there's a question of style here that you should be aware of in induction, and this really comes up to be a big issue here, especially in a theorem like this. It's not uncommon for someone to say, okay, I don't like the fact that I'm using n's because I'm using it there, and that's trying to be my general variable, right? And it's sort of the general case. And so they'll harmlessly introduce an extra variable just to reduce confusion. Like we could do this, assume it is true, the theorem is true for n equals m, and show it implies that it is true for n equals m plus 1. Now the reason I'm not doing this is because we already have enough variables. I don't feel like that adds any clarity. It just makes the variable mess even more of a tangle. So I'm just going to use our raw variables n and n plus 1. Keep in mind when I do this sort of assumption, I am sort of fixing some, in an abstract sense, a value of n, and I'm going to show that at this step n, where it apparently is true, it's going to imply the next one, n plus 1. Okay, some other people might put prime on here, like n prime, something like that. So keep in mind, if you feel like that adds clarity to your writing in induction, go for it. I'm just not going to add extra variables due to the number of variables we already have. Okay, so I'm just going to use n and n plus 1. All right, so really all we have is sort of the nth case. And we have to show that the n plus first case comes out of having the nth case in our pocket. Now to get to the n plus first case, it's easier to look at the left-hand side and realize if we just multiply the left-hand side by another 1 plus x, it goes up to the n plus first case. So that's what I'm going to do. So we already have this assumption, assume the theorem is true for n, and we're going to show it implies it is true for n plus 1. To get to n plus 1, we need to multiply both sides by 1 plus x. Okay, we'll show what we get here. So when we do the left-hand side by 1 plus x, we get 1 plus x to the n plus 1. In the right-hand side, we don't get anything for free yet. We only have the right-hand side multiplied by 1 plus x. So we have 1 plus x. I'll write it down over here. It's a little cleaner. Okay, going from 0 to n. And choose k, x to the k. Okay, and what we need to do is we need to work on this right-hand side here until it becomes the appropriate thing, the n plus first. And so our goal is to get these two n's to change to n plus 1. Okay, or justify that we can change them to n plus 1 when it becomes obvious to do so. Okay, now I have a 1 and an x. So that's actually going to give me two copies of this summation, but with different things in there. Alright, so multiplying by 1 just gives me the original copy of that summation. Okay, so that's from the 1. Alright, now when I multiply the summation by x, that's going to bump up all of the x powers by 1. So instead of x to the k, I have x to the k plus 1. Okay, we're going to have to fix that. That's actually important to fix. There's going to be consequences for fixing that. Okay, so what do we do? Well, what we have here is our goal here is to go from k equals 0 to n plus 1. We eventually want to add together some coefficients, probably coefficients that look like these two, right? To make this n plus 1, choose k plus 1, or something like that, right? All right, so we need to work this out. All right, let's take the one I think that is probably the quickest to change, and that's this particular one right here. Okay, we would like for it to read x to the k. And believe it or not, we can do this in a fairly harmless way. You just have to keep in mind that this summation is just a set of instructions, and we can modify the instructions so we have a k here. Alright, so to do this, I'm going to start with just putting the k, kind of what I want. Right? And then we're going to follow the consequences downstream. Alright, now if this was k, the only thing that needs to be, this needs to be one less than that. Right, so this k, this particular term here needs to be one less than what's in the exponent. So this actually should read as n choose k minus 1. Right, in the summation, these are values of k in the summation going from 0 to n. Right? And effectively, we need to know if I change this to k, what does it do to the entries there? Well, you can make this very sophisticated, but for the simpler ways, what is the first term? Well, if I have 0, then there's a 1 there. So 1. So I'm going to actually start at 1. Okay, what's my last term? If I take an n and put it there, I get n plus 1. So I need to go to n plus 1. Okay, so by changing this exponent here, I do have a bunch of changes I need to make throughout my summation, but these are exactly the same summations. What I've done is the term we call this is you re-indexed it, okay, so that the indices are done differently. I mean, this is a tricky part of the proof. It's actually not mathematical. That's actually a bookkeeping trick. I'm not really doing much math here. I actually just moved the indexing by 1, just so that my terms are the exact same terms there. Alright, turns out I do not have to re-index my left one. Turns out this one's actually in pretty darn good shape. So as of now, I'm going to keep it as is. We're going to need to fix another feature, of course, to combine these. But we are really close to combining these two sums. Okay, now to combine two sums, two index sums, you definitely need your powers of x to have the same indexing. That's the whole point of us changing these to k. But clearly we do have a problem that our indexing starts and finishes are not in the same spots. So what do? Well, actually we can fix each of them in the way we would prefer. So let's go through each fix. Okay, so I'm going to need, I'm trying to allocate space in my head here. Okay. Hold on, let me make sure this thing has good punctuation here. So my equalities here, those are good. Okay. We need about 2 more lines here. Alright, so this starting at 0 is good. But I actually want to go to n plus 1. Let's see if this is actually feasible to do. Notice I just added n plus 1. Okay? Don't want to just recklessly do this, but we want to see if it makes sense. So it turns out we can add this without any harm, and claim that these two sums are the exact same sums. And the reason is n choose n plus 1 is 0. So all I've done by adding this extra term on is I've added a 0. Because that's what I'm doing. I'm adding an extra term. I'm adding the n plus first term in addition to the previous terms here. But that n plus first term is 0. So that's good. So I can keep that. And I want to start at 0. So let's see if that's okay. Okay, I'm not sure if I explicitly stated it in the video yet, but that's okay. If you've been reading the book, you should have seen it by now, but if neither case has happened, when you do n choose k, or n choose a number, if that number is negative, that is by default 0. So again, I've added another term, I added the 0th term, but that is also a 0. Okay, these are sort of the left-hand side zeros on Pascal's triangle. That's where you get the n choose negative numbers. The right-hand side zeros are ones where you do n choose something bigger than n. Those are the right-hand side zeros. Okay, so I've added a term to each of these sums up here, but now our indexing matches perfectly from 0 to n plus 1. And now what I need to do is I need to combine these two sums into a single sum. Okay, going from 0 to n plus 1. These two coefficients add together. And choose k, and choose k minus 1. I do want to write these in an opposite order here in a minute. X to the k. Okay. Alright, now we need to know what that sum actually is. By sum, I mean the addition of these two terms here. So since I have enough space to kind of do it in two, let me go ahead and do this in 2 steps. Alright, I'm actually going to write this one first and this one second. Just to help make connections to what we have up here. Alright, so all I've done is I've switched the order of adding those two coefficients together, because I have no space to do that. And before I tell the answer, let's get all the other stuff written down. So k is going from 0 to n, and I'm going to have some coefficient here, x to the k. N plus 1, sorry. Okay, so there's n plus 1. Alright, so my claim is here, this tool up here helps us decide that. Now you do have to develop this skill of matching who's who, right? Instead of having n choose k and n choose k plus 1, I have n choose k minus 1 and n choose k. So these still are 1 different. This theorem still works perfectly. If these two bottom numbers are 1 different, what we do is it looks like it's the bigger of the two. So in this case, k plus 1, but in our case down here it's k. So we choose k. And the top ones go from n to n plus 1. All right. And ta-da, that's it. That's the right-hand side. Okay, so accomplishment for me here is fitting this proof on one board. But keep in mind, there are some things to digest here. The non-mathematical pieces of reindexing. There's kind of 2 places of reindexing. One is harder, that is this changing the k-index so that it enumerates differently, or seems that way. And then the second step of reindexing is adding these extra 0 terms so that our beginning and starts are compatible with one another. Okay, that's actually the big stumbling block to this proof. The other parts are actually quite simplistic, and in fact, if there's a mathematically hard part, it's this, but I feel like that's not quite as confusing as the reindexing. Okay, so feel free to ask me questions about this sort of thing. This is, of course, not some proof that you would have to do from scratch and memorize, nor is it a style of proof that you're going to have to do something like in this course. I mean, this isn't quite an analysis course, because if this was some advanced algebra course or advanced analysis course, then maybe, but I always get questions, you know, do I have to do this or memorize this proof, or am I going to do proofs like this? No, not really. The whole point of this is it's kind of I owe it to you as part of just learning the binomial theorem. Part of the point of learning proofs and learning about proofs is so you can follow along and see how something is proven, and you can kind of read the proofs and understand them to some degree. But cooking them up is another story completely, right? I can cook this up. This proof is much older than me. Binomial theorem is an old theorem. It's been around for a long time. Okay, there's actually a couple binomial theorems. This is the basic one, but there are other versions as well. For instance, if you check a calculus textbook, you'll see something called the binomial theorem, and they'll change n to some sort of, not just any integer, positive integer, but they'll actually expand on what n could possibly be. And then you have Taylor series and these other cool things. So keep in mind, this thing is built off of beyond just this. Okay, and in another video, we're going to do this proof, not this proof again, we're going to prove the binomial theorem again, but we're going to use a different proof method. We're going to use a combinatorial method to prove it. And the method is going to involve counting words, right? Something we worked on. So we're going to, we've kind of already done this, but I want to do this kind of formally in a single go. We want to think about this as word construction, and the n choose k is the number of ways these different words are built. Okay, so I'll see you in the next one.